So what is A here? A is 0.1 and A naught is 1 e to the power minus K, which is 3.5 times T.
Why is the initial 1? Isn't it 1 times 10 to the power of 11?
You're given the concentration of ClO is the B. O is the A. Wow. That should wake you up.
So how do we know it's 1? Because...
Okay, here's a question. How do we know that A is 1 and A naught is 1 and A is 0.1?
Because it decreases to 10%.
Right, it decreases to 10% of its original value. So then put 100 here and put 10 here. Doesn't matter. Tiffany.
So, like the way that the question was written, how do you know that when they say the rate constant for the reaction, they're talking about K and not K prime? Because I thought it was like, since it was like pseudo first order, they were giving me K prime because it was like the K, the rate constant.
I mean, so whenever people talk about rate constant, they are talking about the observed rate constant.
Okay, so they would specify if they were giving you the pseudo rate constant
Right.
instead.
Yeah. I mean, I don't know the terminology. Maybe you guys are using different terminology in lab. I wasn't using the pseudo rate constant. So this is the rate constant for the pseudo first order reaction.
Yeah, that's K
Okay.
prime.
All right.
Yeah.
Okay. All right.
I just like based it off and thought that 3.5 times 10 to the negative 11 was K prime.
Okay. See, I don't think what did I? Oh, I call this K prime. Did I call this K prime in lecture? In lab, you did that. Okay.
Yeah.
Okay. I'm not using that same terminology here. Okay. All right. Question number 9.
B?
Sorry. Yes, Rachel.
I don't understand still how we get 0.66.
So you're plugging into this equation 0.1. You're plugging into this equation 1. E to the power minus K is 3.5. T is the only unknown.
No, I get that, but like, you're gonna have to take a natural log.
Right.
Can we just like go through that step?
Okay. So this is natural log of 0.1 is equal to natural log of 1 minus 3.5 T. What is natural log of 1? 0. So this is natural log of, so T is equal to natural log of 0.1 divided by 3.5. Okay, plug it into the calculator and you should get that answer. Questions? Yes, Chris.
I don't know if someone already asked this, but I still don't understand why is it 3.5 and not 3.5 times 10 to the negative 11?
3.5 times 10 to the negative 11 is this quantity here. Multiply that by the concentration of B, which is given.
Oh, okay.
And that gives you the observed rate constant. Question number 9. B. Question number 10. A.
Can we go over that? Can we go over that?
You want to go over that one? Okay. I'm going to try to do something that I did about a year ago, and I haven't done that recently. Yes.
Could you repeat the answer 9?
Number 9 was B. All right. So okay, let's just. I'm going to just write it out. I'm not going to solve it.
It might if it goes like.
Professor, does it matter whether I use Celsius or Kelvin?
Oh, it does.
Oh, okay, that
Yeah.
probably explains why.
Okay, always work in kelvins. Okay, the only time that you should work with centigrade is if you're looking at temperature differences. And then, you know, you can take the temperature difference in centigrade and say it's the temperature difference in Kelvin. Otherwise, anytime you're doing science, you should be working with Kelvin.
Okay,
So, but let me just say that log of K is equal to log of A minus E sub A over RT. This is the equation that you need to use to solve question number 10, which will give you answer 8. Yes, good.
I have a quick question, question number 10. I got the right answer, but I did it in the opposite way because I first solved for it and I got the negative value, and so then I realized that ln of, like, it should be 48 over 4 rather than 4 over 48. So I'm wondering, is that because, like, is the 48 above because the rate would be, because it's talking about hours? Is that why you reverse them? I don't, not entirely certain why I got that.
Let's make this log of K2, this is 2, this is log of K1.
Yeah.
Is equal to log of A.
Or is it just that you divide, you subtract? Oh, because it's the final. I'm being silly. I got it.
Okay. All right. Everybody happy? So you subtract the 2, you get log of K2 over K1 is equal to minus E sub A over R 1 over T2 minus 1 over T1. You just plug into this equation and you get the answer. Okay, let's begin our lecture.
Extremely exothermic and proceeds with a shower of white sparks. A small amount of a white mixture of potassium chlorate and sugar is placed on top of the iron oxide aluminum mixture. A few drops of concentrated sulfuric acid are added to the chlorate sugar mixture to start the reaction. The reduction is extremely exothermic and proceeds with a shower of white sparks. The crucible becomes red hot. The aluminum has reduced the iron oxide to iron. When we look into the crucible, we see a ball of white hot iron glowing at the bottom. When the crucible has cooled, we can remove the iron produced by the reduction of iron oxide and show that it is indeed iron by picking it up with a magnet.
So this reaction illustrates thermodynamics. Very, very exothermic reaction. Let's look at a reaction that illustrates kinetics.
In this experiment, we are looking at the explosive decomposition of a compound of nitrogen triiodide. This brown compound is so sensitive when dry that just touching it with a feather causes an explosive decomposition. It forms nitrogen and iodine. Like this mousetrap, which releases potential energy from the spring, the nitrogen triiodide releases chemical energy. when it decomposes into its elements, nitrogen and iodine.
This is also a very thermodynamically favored reaction, but it's also a very fast reaction. Okay, so let's get back on track here. Let's look at the outline. Okay, so today the goal of the entire lecture today is to understand where does this equation come from. What is this equation called? The Arrhenius equation. That's the equation from which we get that.
Okay.
What is K here?
Rate constant.
Rate constant. This is lowercase k. Let me make that very clear here. Okay, lowercase k. Capital A is the pre-exponential factor. E to the power minus E sub A over RT. E sub A is the activation energy, R is the gas constant, and T is the temperature expressed in kelvins. One way to understand what A is to say that it is the rate constant for a reaction that has no activation energy. If you have no activation energy, what is this going to be equal to? 1. Then K would be equal to A. So you can say that A is the rate constant for a reaction that has no activation energy. All right, but we're going to get a more thorough understanding of A. So this is the experimental data that you find when you look at the rate constant versus temperature. Actually, I have a few extra handouts. Does anybody need a handout? Oh, wait, what did I give you? Okay. So, want to be there. Oh, you are, sorry. Did you get the whole handout?
I think so.
No, I think you missed it. Okay, yes. All right. So this is what you observe experimentally. You measure the rate of a reaction and plot it against temperature. This is what you get. Remember, the rate of a reaction is R is equal to K times A times B. So when you're plotting the rate versus temperature, you're really plotting the rate constant versus temperature, because these two quantities are not dependent on temperature. The entire dependence of the rate on temperature is due entirely to the dependence of the rate constant on temperature. And this is how Arrhenius fit this experimental data. This is purely an empirical equation. Today we're going to see that there is a theoretical basis for that equation. So if you want to get a straight line, what should we plot on the y-axis? What do we plot on the y-axis? The natural log of k, and on the x-axis? 1 over t, and the slope is? Negative E sub A over R. So what we're going to do is to try to use collision theory of chemical kinetics. This is the simplest, this is the crudest model that we can think of. Essentially, we're going to think of molecules as billiard balls banging into each other, And we're going to think of these as elastic collisions. There are much more sophisticated models for understanding how the rate depends on temperature, and you will encounter those when you take your first semester Chem course. But today, we're going to think of molecules as not having any structure. We're going to assume that the molecules are not vibrating. We're going to assume that the molecules are not rotating. All of these are huge assumptions that are incorrect. But we are able to get a very simple understanding of what's going on. So we're going to think about the molecule of interest, the orange molecule, colliding with the blue molecules. And any blue molecule that is outside this cylinder here, whose radius is twice the radius of this orange ball. If the blue molecule is outside this cylinder, the orange molecule is going to miss. Otherwise, it's going to hit that blue molecule. So you can do a simple calculation, and I'm not going to do that here in this course, but you will when you take a Chem course. And if you do that simple calculation, you will find that the number of collisions per second is going to be proportional to the concentration of A molecules and the concentration of B molecules. So we are looking at this reaction here, A plus B going to some product. And what I'm saying is that if I count up the number of collisions per second that occur between the orange molecules and the blue molecules, the number of collisions per second is going to be proportional to the concentration of A and the concentration of B. So here is an illustration of that. The frequency of AB collisions involving one A molecule is going to be proportional to the number of B molecules. If you double the number of B molecules, the number of collisions that this one A molecule makes is going to double. You can say the same thing if you reverse what I just said. So what we're going to say is that the number of collisions per second is proportional to the number of A molecules and B molecules. To be more specific, the concentration of A and the concentration of B. So the number of collisions per second is proportional to the concentration of A multiplied by the concentration of B. But we're going to assume that every collision leads to a reaction. So the reaction rate has to be equal to the reaction. The reaction rate has to be equal to the collision rate. So the rate of the reaction is proportional to A times B. I can get rid of that proportionality constant and put a C in front. That's where the rate constant K comes from. Yes, Neha.
What did you say we were going to assume again?
We're assuming that every collision leads to a chemical reaction. So the rate of the reaction is going to be the same. Actually, I should have put equal here. The rate of the reaction is going to be equal to the number of collisions per second, which is proportional to A times B. We get rid of the proportionality constant and proportionality and put a proportionality constant here. But if this was true, Because there are 10 to the power 29 binary collisions per second in 1 liter of volume, every reaction in the gas phase would be over in 1 nanosecond. If we assume that the rate is equal to the number of collisions per second, which means we're assuming that every collision leads to a chemical reaction, then we can calculate the number of collisions per second based on simple kinetics of gas molecules moving around. There are 1 times 10 to the power 29 binary collisions per second in 1 liter of volume. This is an easy calculation to do. So if you assume that every collision leads to a reaction, then every gas phase reaction must be over in less than a nanosecond. But we know that's not true. So we have to invoke the concept of
Activation energy?
Activation energy, which says that not every collision leads to a chemical reaction. If you have an energy less than a certain minimum, then the two molecules collide and bounce off each other. Only if you have an energy greater than that certain minimum, which we are going to call activation energy, the two molecules collide and produce two new molecules. So this equality is not true. So we assume that the two reactant species come together and form an activated complex or a transition state at the very top here. This entity lasts for times on the order of femtoseconds. What is a femtosecond? 10 to the power minus 15 seconds. That's the time scale for which this species exists. There are very few laboratories in the world that can characterize a transition state, because you have to take a picture with a camera that operates at 10 to the power minus 15 seconds. All right? So two reactant molecules come and form a transition state whose energy is above the reactants, and that's why you have this activation energy. And when you get beyond the activation energy, you end up with the products. So this is the minimum energy that the two molecules must have when they collide with each other to form the product. So if you think about a container full of gas molecules, these gas molecules are going to have a spread in speeds, and if you plot on the y-axis the fraction of the molecules and on the x-axis the kinetic energy, few molecules are going to have very low kinetic energy, very few molecules are going to have very high kinetic energy, most molecules are going to have an energy intermediate. So this curve here is called the Maxwell-Boltzmann distribution. Boltzmann is the same Boltzmann that we used for the Boltzmann equation. Maxwell is the Maxwell coffee. Same Maxwell, I mean the spelling, okay? It's actually, the Maxwell is the guy who came up with the Maxwell's equation for electromagnetics. Okay, you might have heard of the 4 equations in electromagnetics. So,
What's it called?
Maxwell-Boltzmann distribution. Okay, so this is what it looks like. This is at low temperature. If you heat up the gas, you get a different distribution, and the distribution shifts to the right. And what this graph is showing you is that the number of molecules that have an energy greater than a certain minimum here, we're going to call this our activation energy here. The fraction of molecules that have an energy greater than that activation energy is given by the area here. The fraction of molecules that have an energy greater than the activation energy is given by the area under this curve here to the right of this vertical line here. Yes, Neha?
What does that mean? Because like you said that if it gets past the activation energy, then it can produce products. But
Yeah, so here I'm not looking at any products here. I'm just looking at a collection of gas molecules in a container. And I'm arbitrarily saying that for another chemical reaction occurring in another cylinder, the minimum energy, the activation energy, let's say, is this amount. So I'm trying to figure out in this just one gas container that has only one set of molecules, what fraction of those gas molecules have an energy greater than that minimum energy. So the area under this curve here represents the total number of molecules. So this area here divided by the area under that entire curve is going to be the fraction of molecules that have an energy greater than that minimum energy. Yes, Rachel?
Does that mean that that fraction of molecules that have the minimum energy available are able to react?
Right. Okay? This is the fraction of the molecules that can react. If it were in another container with another molecule, set of molecules. But what do you see here? When you increase the temperature, what happens? Yes, Tamara?
When you increase the temperature, the activation energy is the same, but the number of molecules that have reached the activation energy and completed the reaction are more for the higher temperature.
Exactly. The number of molecules that have an energy greater than the activation energy increases rapidly with the temperature. So as you increase the temperature, the area under this curve becomes larger. That's why rates of chemical reactions increase with temperature. Let me repeat that. The reason why chemical reactions increase in rate is because the fraction of molecules that have an energy greater than the activation energy increases with temperature. The number of collisions also increases with temperature. But that's not the dominant force. The dominant force is the fraction of molecules that have an energy greater than that barrier. Okay? And it can be shown that the fraction of molecules that have an energy greater than that barrier is this quantity here. So what I had here was the number of collisions per second. If I have this factor added in, now I have the rate.
So this is the E to the power of negative activation energy over R2 greater than
It represents this area here. The blue area here. Yeah, but it also represents the red area at a higher temperature. The red plus the blue for the higher temperature. Questions?
C is just the proportionality.
Exactly. All right? We're not done that yet. We're not done yet. Even with this modification, the observed reaction rate is much, much less than the rate of collision with energy enough to surmount the barrier. So this still doesn't give us the right answer.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
So if you look at the reaction between O3 and NO, even if the two molecules have sufficient energy to overcome the barrier,
if the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted. If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
Replay that over again.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
So there is an additional factor which we are going to call the steric factor. I like to call it the fudge factor, but that's off the record. Sorry? So look at the reaction between these two molecules, two NOCl molecules to form NO and Cl2. If they collide like this, no reaction occurs. But if they collide like this, then a reaction occurs. So not only must the molecules have enough energy to surmount the barrier, they must also have the right orientation. And that steric factor P, which takes into account the orientation, can vary from values such as 0.16 down to 10 to the power minus 6. Here's the steric factor for several different gas phase reactions. So now I have to change my rate equation. It's going to be C times A times B times the fraction of molecules that have an energy greater than that barrier, but now I have to include the steric factor, which takes into account orientation. Yes, Rachel?
What exactly do the numbers represent? Steric factor, but what do they count?
So what this is saying is that if you look at what fraction of the molecules with enough energy react, for this reaction it's 0.16. For this reaction it's only 10 to the power minus 6. Okay?